Let us look at another problem which also deals with the rectangular coordinate system. So a particle travels along the parabolic path y is equal to bx squared. Its component of velocity along the y-axis is vy equals to ct squared. We're asked to determine x and y component of the particle's acceleration, so ax and ay, and we know that b and c are constants. So here we're given the equation of the curve, y is equal to bx squared and vy, and so we're asked to find the acceleration components. So the very first step, again, is to write down what we know, either from the given of the problem or from the different equations we have at hand. Remember, if you do not know all the equations by heart, you can simply check the formula sheet that's available at the end of the book. So we know that y is equal to bx squared and that vy is equal to ct squared. And we know the fundamental equations, namely that v is equal to ds over dt. So if we want to write that in terms of y and x, we can simply write that vy is equal to dy over dt. And then for a equals to dv over dt, we can write that ay is equal to dvy over dt. So as you can see here, since we're given y and vy, by making use of vy, we can simply take its derivative and get the value of ay. But we're still looking for the second component of a, because remember we're dealing with a rectangular coordinate system, and so a is written as a is equal to axi plus ayj. So far we've solved half of the problem, so we know that ay is equal to dvy over dt, so we can simply take the derivative of vy to find ay. But what about ax? How can we actually find ax? To do so, we need to know vx first. And so the step 2 is to find an expression for vx. We know that vy is equal to dy over dt, and so dy is equal to vy dt. Now remember, we only have an expression of y as a function of x and not an expression for y as a function of time. But it would be actually useful to have an expression of y as a function of time, since knowing that we can translate x to an equation of time by simply making use of the equation that relates both variables together. So let's see that. We have that dy is equal to vy dt. So taking the integration both sides, we have y minus y0 is equal to the integral of vy dt from t0 to t. Then vy is equal to ct squared from t0 to t. Replacing all that, we get y minus y0 is equal to ct cubed over 3. Then noting that y0 is equal to 0, we have that y is equal to ct cubed over 3. So that's great. We have an expression for y as a function of time. We have an expression of y as a function of x. So by combining both equations together, we should be able to get an expression of x as a function of time. And so once we have an expression of x in terms of time, we can simply take the derivative once to get vx and twice to get ax. So we have y is equal to bx squared, so x squared is equal to y over b. Replacing y with the expression ct cubed over 3, we have x is equal to square root of ct cubed over 3b, from which we can take the derivative. So vx is equal dx over dt. Taking the derivative of x with respect to time, we get vx is equal to square root of c over 3b times 3 over 2 times t to the power 0.5. Again, for step 3, we need to find ax. We can simply take the derivative of vx. So ax is equal to dvx over dt, which is equal to 3 over 4 square root of c over 3b times 1 over square root of t. So that's the expression for ax. We know how to find an expression for ay, which is the derivative of vy. So derivative of ct cubed over 3 is simply equal to 2ct.